Thanks for joining my session. Today, I'd like to talk about how and why we migrated our inter-microservices communication method from HTTP to gRPC, especially in our Ruby microservice. My name is Nao, and I work at Vantage from Tokyo, and I work as a software engineer at the infrastructure team. My team has two responsibilities, SRE and development infrastructure, and why I worked on introducing of gRPC in the microservices. In this talk, I'd like to talk about those three things. The first one is why we decided to introduce gRPC. And the second one is about how we migrated from HTTP to gRPC. And the third one is what we achieved by using gRPC. Okay, let's start from why. At first, as a background, let me introduce my company's products. We have several products. Vantage Visit is a product for jobs and candidate matching, and Vantage People is a product for professional contact management. By these products, we offer our user experience like LinkedIn based in Asia. These products are on one platform, which means they share the same set of users' profile data, so user profile data is very important for our products. Our products are built with more than 100 microservices. They are written in Ruby, Go, Python, Node.js, etc., and run on the Kubernetes cluster. We have been using H1 for majority of our microservices. As I said, user profile data is very important for our products, and it is managed by a service we call user service. So this service is very important for us. This service is written in Ruby by historical reason, and today I focus on this service. Let's dig into the details of user service. User service is a microservice used to get or update user profile data. This service treats fundamental data, so used from many microservices, and high throughput is required. And this service's latency often directly affects the user experience, so low latency is also required. This service was widely used in the microservices, but there was a problem. So what was the problem? The problem was the latency caused by using H1. Without keep alive, H1 does not perform well for several reasons. For example, DNS lookup and TCP/3 handshake is necessary. They increase the latency. And the TCP slow start is also a problem. We reduced the server-side latency as much as possible, but it was not enough to meet the increasing demand. So we decided to introduce gRPC. Why gRPC? As you know, there are some RPC frameworks in the world, and we could choose a suitable one. In that situation, we decided to use gRPC by those three reasons. The first reason is high performance. gRPC is built on H2, and so it can use long-lived, real-time communication streams. This gives us low latency and high throughput. The second reason is protocol buffers. gRPC uses protocol buffers. It provides a single source of truth of gRPC service definition. It is a very good point, and as an additional good point, we were already using protocol buffers over H1 before using gRPC. So it was a very natural choice for us. And the third reason is multiple language support. We have microservices written in several languages such as Ruby, Python, Go, Node.js, etc., and the gRPC supports these languages. It was a very important point. For these reasons, we chose gRPC. Okay, the next topic is how we migrated from HTTP to gRPC. How we migrated? Looking back, I think there were two steps. The first step is preparation, and the second step is migration. Let's start from the preparation step. For using gRPC, there are 4 required preparations: schema management, monitoring, productive development environment, and load balancing. Right now, the gRPC ecosystem is not so mature enough, so especially in Ruby, so we have to think about those things. The first one is schema management. Without a monorepo, which means under the system maintaining multiple repositories, we have to share the same prot files across the multiple repositories. So how should we share prot files? A few approaches we can take here. For example, copy and paste manually. In this approach, it's very hard to update multiple repositories continuously, or download prot files automatically in each repository. In this approach, you still need to generate code manually for each repository. So you will suffer from the differences in each developer's environment, for example, version of proto, presence of plugins, etc. So we decided to make a central repository for prot files. APIs. This is a central repository for schema management. API stores all prot files for our company and do various tasks in the CA pipelines. How to use APIs repository? In this repository, code is automatically generated in the CA pipelines. Ruby, Go, and Node.js code is generated for each prot file. Then, generated code is distributed via package managers, such as Bundler, Go modules, and npm. With this workflow, developers don't need to generate code by themselves and can focus on the implementation of features. This is an example code in APIs. Ruby code are generated and published at RubyGems. By using Bundler, developers can fetch and use the generated Ruby code. So, with this workflow, how we develop gRPC servers and clients in Ruby? For gRPC servers, we implement a class which inherits a generated gRPC service class fetched from APIs. By implementing instance methods for each RPC method, we can use gRPC servers written in Ruby. And for gRPC clients, we use a stub class fetched from APIs. By using a stub object like this, we can communicate with gRPC servers in Ruby code. This is the basic usage of APIs, and we develop gRPC servers and clients like this. Okay, and the next topic is monitoring. As you know, application monitoring is required in production. As a background, we were using various SaaS products such as Datadog, New Relic, Honeybadger, etc. for monitoring our H1 servers. We wanted to continue to use them for gRPC servers. How to monitor gRPC servers? For this purpose, we can use gRPC interceptors. We need to send metrics of each gRPC request, and with gRPC interceptors, we can implement such features. gRPC interceptors are used like this. There are client interceptors and server interceptors. Client interceptors are executed on the gRPC client around the user code, and server interceptors are executed on the gRPC server before the request is passed on to the user's application logic. It is a perfect way to implement command patterns, for example, logging, monitoring, authentication, etc. So we can use gRPC interceptors for monitoring. But gRPC interceptors for each SaaS product are not officially provided at this time, so we had to implement some gRPC interceptors by ourselves. We implemented them and made them available to the Ruby community as open source software. The published interceptors are shown here. For example, we implemented a gRPC interceptor for New Relic. With this gem, we can send metrics to New Relic in each request. And the other one is a gRPC interceptor for Open Sensors. With this gem, we can send metrics to some SaaS products supporting Open Sensors. And another one is the gRPC interceptor for access logging. With this gem, we can print access logs in a specified format. By these gRPC interceptors, we monitor our gRPC servers. Okay, the next topic is productive development environment. As you know, it is a very important topic. And now, we need to create a productive development environment for gRPC by ourselves. For H1 servers, the ecosystem is mature and many open source libraries exist, so we can use them. But this is not the case with gRPC servers, especially in Ruby. We need to create a productive development environment by ourselves. So, how to create such an environment? For the productivity, we use a common utility library named servicex. We want to use some useful features, for example, hot reloading and utility for protocol buffers, and we want to avoid repeating the same configuration in multiple microservices. So we implemented a common utility library named servicex. Servicex is used by all gRPC microservices in our company. I'll show you some useful features of servicex. For gRPC servers, we implemented gRPC server command. This is used like this. We execute bundle exec gRPC server, then a gRPC server process starts to run. It prints some logs and starts to listen on port 6046. With this command, gRPC service class is automatically loaded and some gRPC interceptors are automatically set. After reloading feature is also implemented. With this command, developers can just focus on the implementation of gRPC service classes. And next, for gRPC clients, we implemented servicex gRPC stub from method. This is used like this. With this method, some gRPC interceptors are automatically set and the user agent is automatically configured. So developers don't need to do complicated configuration, so they can just focus on implementing the business logic. And next, for using protocol buffers in Ruby, we implemented a utility library named PB. With PB, we can create protobuf objects more easily. For example, as shown here, we can create a timestamp object from a string object in the easy way. Without PB, we have to convert a string object to a time object by time.parse method, then pass it to the Google protobuf timestamp class as an argument. On the other hand, with PB, we don't need to do such complicated things. By passing a string object to pb.toTimestamp method, we can get a protobuf timestamp object easily. And the pb.toProto method is also useful. With this method, we can create a user-defined protobuf object from hash object. As shown here, the values of hash objects are automatically converted to protobuf objects, so we can create nested protobuf objects in the easy way. PB is included in servicex, but we made it available to the Ruby community as open source software. So if you are interested, please try it. That's all for servicex. And the next topic is Ruby on Rails. For productivity, we decided to use gRPC combined with parts of Ruby on Rails. As background, we migrated from Ruby on Rails and wanted to keep using parts of features in it. So we decided to use gRPC gem with Rails gem. And we found that it's very useful to build a gRPC server with part of Ruby on Rails. So we recommend this configuration if you are in the same situation. And next, let's think about the load balancing. What should we consider for it? For gRPC, L4 load balancers aren't very useful. As you know, gRPC is built on H2, which is designed to have a single long live TCP connection. So in L4 load balancers, once the connection is established, there's no more balancing to be done. Our request will get pinned to a single destination. This is not a good situation. So we use Istio for L7 load balancing in Kubernetes clusters. As shown here, envoy containers configured by Istio are injected as sidecar proxies and used for L7 application level load balancing. By this configuration, the load is evenly distributed. Okay, I explained the preparation step. Next, I'll introduce our migration step. So, how we migrate it? In the migration, our basic strategy was try small. At first, we made a prototype as a proof of concept to quickly see the impact. And then next, we used gRPC for our part of the traffic in production and gradually increased the percentage of the gRPC. This is a schematic diagram of POC. We have a development Kubernetes cluster. This is separate from a production cluster, and we tried gRPC in this cluster. By using a development cluster, we could try gRPC without worrying about affecting production environment. This is the result of POC. This diagram shows the distribution of latency. As shown here, latency decreased dramatically in all cases. By seeing this result, we decided to try gRPC in a production cluster. So, how we tried gRPC in production? This is a schematic diagram of our trial of gRPC in a production cluster. At first, we used gRPC for only a small part of the traffic. By trying small, we could minimize the preparation cost to minimize the risk. And then next, we gradually increase the percentage of gRPC. By gradually increasing the traffic, we could control the risk. And finally, we could achieve the complete migration. With these steps, we migrated to gRPC. Okay, and next, let me introduce the result achieved by using gRPC. As a result, we've achieved the performance improvement. By using gRPC, average latency decreased dramatically. Average latency decreased by about 20 milliseconds per request, and the impact was more remarkable when many requests to user service were involved in one web transaction. For example, as shown here, in some microservices, average latency decreased by a half. The brown one is the latency when using H1, and the red one is the latency when using gRPC. Average latency decreased from 130 ms to 65 ms by switching to gRPC. In this microservice, multiple requests to user service were involved, so the impact was remarkable. So, by using gRPC, we could achieve a performance improvement and improve the user experience. And next, let me introduce what we are doing since the migration. After the success of the migration from HTTP to gRPC and the achievement of performance improvement, the use of gRPC is increasing throughout the organization. Now, almost all clients of user service are using gRPC, and new microservices are being developed using gRPC. And gRPC started to be used in other languages, for example, Go, Node.js, etc. So gRPC is becoming widely used in the organization. This is a summary of this talk. At first, I talked about why we chose gRPC. And the answer is what we needed a high-performance RPC framework, and gRPC was performant enough. And another reason is that we were already using protocol buffers, so it was a natural choice. And we also needed multiple languages support because we had microservices written in several languages. gRPC supported them. It was a very important point. And next, I talked about how we migrated from HTTP to gRPC. By using gRPC, we have created a workflow for protocol buffers using our APS repository. And we have also developed some libraries for productive development environment of gRPC and published some of them as OSS. And in the migration step, the basic strategy was try small, so we tried in a small and quick way. Then we could achieve the migration. At last, I talked about the result of migration from HTTP to gRPC. By using gRPC, we could achieve the performance improvement. Now, the use of gRPC is increasing throughout the organization. That's all. Thank you for listening.